Hello students, very good afternoon to all of you. So today it's fixed beam that I will explain. So first of all, what is fixed beam? Fixed beam is that this is a simply supported beam, and under this load the beam will deflect like this. So now if I want to reduce these deflections at both the ends, this theta to 0, then I will apply a moment like this. So that will try to rotate in the reverse direction so that this slope will become 0 at both the ends. So in this case, the deflection will be like this. So to provide a fixity at both the ends, what we do? We provide fixity at both the ends so that the rotation becomes 0 at both the ends. So this is fixed beam, and this one is simply supported. So to reduce the deflection at the center, suppose this is 25 mm, in this case maybe 11 mm, like 10 mm, and this slope, this theta, this rotation here, this becomes 0. So here my tangent to the curve is along this horizontal line, whereas there is a rotation of theta. Suppose this is theta A, this is theta B. So in order to reduce the rotation at 0 at both the ends, we built both the ends are encasted, or we can say both the ends are fixed. So this is fixed beam. So in summary, let us start from the basics. What is statically indeterminate beams? Statically indeterminate beams is that, first of all, statically determinate. Determinate structure are those structures which can be analyzed by the three conditions of equilibrium. That is, sigma v is equal to 0, sigma h is equal to 0, and sigma m is equal to 0. Means algebraic sum of all the vertical forces should be equal to 0, algebraic sum of all the horizontal forces should be equal to 0, and algebraic sum of the moment should be 0. So these are the three conditions of equilibrium. For statical equilibrium, there are three conditions. So what happens in case when our structure cannot be analyzed by these three conditions of equilibrium? Then we can say my structure is statically indeterminate. So indeterminate. This fixed beam is also indeterminate because this cannot be analyzed by the three conditions of equilibrium. In this case, I have four unknown. One is, this is a moment MA, this moment is MB, there is a reaction at A, reaction at B. So since no horizontal forces are acting, so I have four unknown: RA, RB, this MA, and this MB. I have four unknown, and since horizontal forces are not acting, so I am not taking that. So out of these three conditions of equilibrium, this minus this, I have two conditions of equilibrium which are available. So four unknown and two conditions, sigma v and sigma m is equal to 0. Since I am not considering sigma h because no horizontal force is acting, so I am taking 2. So 4 minus 2 is equal to 2. Means this fixed beam is statical indeterminate of 2 degrees. So degree of indetermination is equal to 2. So statically indeterminate beams determinate if the reactions component can be calculated by three conditions of equilibrium. These are three conditions of equilibrium. And when the number of unknown reactions component exceeds the static condition of equilibrium, the beam is said to be statical indeterminate. In this case, the reaction components at the support will be determined by the equations of deformation or displacement in addition to the equation of statics. My means condition of compatibility is also required, or you can say condition of deformations in addition to the statics equilibrium. So for analyzing the statically indeterminate structures, what we require in addition to the statical equilibrium conditions, sigma v is equal to 0, sigma h is equal to 0 and sigma m is equal to 0. So in addition to these three statical condition of equilibrium, I require another conditions, that is condition of compatibility, or you can say condition of deformation or displacement in addition to the statics. So what is that? I will explain shortly. First of all, let us see these are the determinate structures. In this simply supported beam, I have had two unknown, RA and RB, and two conditions are available. Sigma h I am not taking. So two conditions of equilibrium are available and two unknowns. So 2 minus 2 is equal to 0. In this case, I have a two unknown here. One is this reaction, another is this moment. So two unknown, and condition of equilibrium is sigma v is equal to 0, sigma m is equal to 0. So two condition of statical equilibrium are available and two unknown. So 2 minus 2 means 0. So this is statically determinate structures. In this case, if you see, this is a simply supported beam and there is a couple at the center. So I have two unknown. I have two unknown. One is this, another is this, RA and RB. So total unknown 2, and condition of equilibrium is sigma v is equal to 0 and sigma m is equal to 0. So condition of equilibrium available is 2. So 2 minus 2 is equal to 0. So this is also statically determinate. Similarly, this is overhang portion. So I have two unknown. One is this, another is this. RA, this reaction at two reactions are available to be calculated, and condition of equilibrium is sigma v is equal to 0, sigma m is equal to 0. So two condition of equilibrium available and two unknown reactions. So this one is also statically determinate. Let us see in this figure. I have two unknown. One is this one, another is this one. So I have two unknown, and condition of equilibrium available is equal to 2. Sigma v 0, sigma m 0. So this also is statically determinate. Now statically indeterminate. You see, this is a propped cantilever. See, propped cantilever. So in this case, I have a known. One is this reaction, another is this moments. So two unknown here, and one unknown is also here. So total number of unknown reactions to be calculated is 1, 2 and 3, and condition of equilibrium available. Condition of equilibrium available is equal to 2. Sigma v is equal to 0 and sigma m is equal to 0. So this 3 minus 2 is equal to 1. So we can say this is a statically indeterminate structures of 1 degree. So it is degree of indetermination is equal to 1. So this propped cantilever is indeterminate structure of 1 degree. Now let us see this fixed beam. In this case, so I have a, this is a fixed beam. So I have this fixed beam. I have 4 unknown. One is this reaction R1, second is R2, and this moment and this moment. So 2 plus 2, 4 unknown. So unknown is 4, and condition of equilibrium available is 2. Sigma v is equal to 0, sigma m is equal to 0. So it means this is a indeterminate structure of 2 degree, 4 minus 2. So degree of indetermination is 2. Now let us see this is so this is a continuous beam. So in this case there are 3 unknown. Reaction here, this is R1, R2 and R3. So I have 3 unknown reactions and condition of equilibrium available is equal to 2, sigma V 0 and sigma M 0. So this is a indeterminate structure of 1 degree. So its degree of indetermination, static indetermination is 1. So now probed cantilever, this is my probed cantilever. So in this case there are 3 unknown. One is this reaction, this RA, RB and this moment MA. So there are 3 unknown. So 3 and condition of equilibrium available is 2. So I am not taking sigma H since no horizontal load is acting. So statical equilibrium available sigma V 0 and sigma M 0. So its degree of indetermination is 3 minus 1, 2. So this is a probed cantilever. In this case also I have 3 unknown, this plus this and condition of equilibrium available is equal to 2. So 3 minus 2 is equal to 1. 1 degree of static indetermination is there. So hence the beam is statically indeterminate to first degree. So equation of compatibility or continuity of deformation is required in addition to the condition of statics. That is, what is this? In this case also, if I remove this, then my beam will deflect like this, and this probed cantilever, these probe reactions will try to reverse its rotation like this one, so that my net deflection is 0. It means whatever deflection due to this load at this point, so the same deflection will be produced by this probed reactions. So whatever deflection will be due to this load, that same will be counter balanced by this probe reactions, so that my net deflection is 0 here. So this is condition of compatibility, a condition of deformation that is required to analyze this statical indeterminate structure. So for the analysis of the indeterminate structures, what we require? We require condition of compatibility in addition to the condition of equilibrium. Now fixed beam, let us explain this. Fixed beam is built-in beam, or we can say encasters. So both the ends are fixed. Rotation is reduced to 0. This rotation is 0. So there is a fixity at both the ends, so that the rotation is 0. this will try to deflect like this, and this moment due to fixed end will try to this moment will try to reduce the rotation to 0, so that this slope become horizontal here. So this is the deflected shape. So in this case I have 2 point of contraflexure when the radius of where curvature is changing. Where the curvature is changing, this is R, and for this portion it will be this. So this is the point when the curvature is changing. So this is a point of contraflexure. So I have 2 point of contraflexure in the case of fixed beam. One is this, another is this. So ends A and B are constant, are built in. So reaction component is equal to 4. One is this reaction RA, MA, RB and MB. So I have 4 reaction components. So equation of statics available is equal to 2 sigma V0 sigma M0. So static indeterminacy is 4 minus 2 is equal to 2. So fixed beam has statical indeterminate of 2 degree. This is what I have explained so far. Continuous beam. So this is a continuous beam. In this case, equation of statics is 2 and reaction component 3. So this is 3 minus 1 is 1 degree. So static indeterminacy is 1. In this case also, I have 4 reaction component 1, 2, 3, 4, and equation of statics is equal to 2. So static indeterminacy is 4 minus 2 is equal to 2. Same, this is 1 reaction and this moment 2, 3 and 4. 4 reaction component. Equation of statics is equal to 2. So static indetermination is equal to 4 minus 2 is equal to 2. Similarly, in this case, I have 5 reaction component. One is MA, RA, RB, RC and this one. So 2 reaction component both the ends, 2, 4 plus 1. So 5 reaction components are there, and condition of statics available is equal to 2. So static indeterminacy is equal to 5 minus 2 is equal to 3 here. So I will say this is a continuous beam of 3 degree of static indeterminacy. Now a fixed beam. A fixed beam is one in which ends are built in, are clamped, so that the tangent at each end remains horizontal. So the ends are clamped, are built. So this tangent here and both the ends are horizontal along this beam. So when the beam is subjected to external load, hence a fixed beam is a simply supported beam subjected to end moments of such magnitude that the slope at each end is 0. Like this, I can also visualize like this. This is a simply supported beam with this reactive couple. So this will deflect like this, and this will deflect like this. So there is a hogging moment and there is sagging. So the net effect is that this slope here is reduced to 0. If I draw a tangent here, it will be along this horizontal line. So the end reacting moments are known as, these reacting moments are known as fixed moments. Suppose this is B, MA and MB. These are my fixed moment. Let us see, there is a simply supported beam of distributed load like this. So there is a reaction R1, R2 and fixing moment M2, M1. So under this loading, this will deflect like this. My beam will deflect in this way. So if I draw a tangent here, there is a rotation of, this is, suppose this is I1 and this one is I2. So this is the rotation here. If I draw the bending moment diagram, it will be parabolic. The free bending moment diagram we can say mu diagram. Now due to this effect, due to fixing effect, my beam will deflect in the reverse direction, in the upward directions. If I draw a tangent here, so it will rotate in this way. And similarly, as the net effect is 0 here, slope is 0 here, it means this rotation should be equal to this rotations. So if this is I1, this one is also I1, I2. So same amount of rotation at both the ends will be there, but that will be in the reverse directions, so that my net rotation at both the ends are 0. This is what fixing moment do in case of fixed beam. So the end moments are the reacting moment try to prevent the rotation or slope at each end to 0. So net effect is 0. So this rotation is equal to this upward rotation, or I can say so if I apply a moment, so that this rotation becomes like this, this is reacting moment. So fixing moment diagram or mu dash diagram will be like this. Suppose this is M1 and this is M2. Since both are hogging, so it will be M1, M2 minus. If I superimpose both the diagrams, that this free bending moment diagram and the fixing moment diagram, if I superimpose both, then I will get this one. This is my free bending moment diagram, and this one is fixing moment diagram. This one is sagging and this is hogging. So my net diagram will be like this. It will be hogging here, and there is a sagging effect. This one is also hogging. So this is my net bending moment diagram. I have superimposed both the free bending moment diagram and fixed bending moment diagram, and the net deflection will be like this. So I have 2 points of contraflexure. One is this, one is this, where my curvature gets changed. So this is the deflected shape, and the effects of fixed will be this way. So the net bending moment will be mu x and mu x dash, means free bending moment and fixed bending moment. So if I want to know the net bending here at a distance of x from this support, this is the x section. So at this, my net bending moment diagram will be this one, this mu x is a free bending moment diagram, and this one. This one is my fixed bending moment diagrams. So if I add both, mu x plus mu x1, I will get net bending moment at a distance of x. So free plus fixed is equal to net. So effect of fixed at the end is to reduce the bending moment diagram. Since this one is hogging and this is sagging, had this both the ends are not fixed, as in a simple supported beam, my rotation will be like this. But after providing the fixed T, its deflected shape will like this. So the deflection get reduced and rotation becomes zero at both the ends. So effect of both are reverse. This is sagging bending moment diagram and there is a hogging. So sagging minus hogging, it means net bending moment diagram get reduced in case of fixed beam. So the effect of fixed T at the end is to reduce the bending moment. Now bending moment for a fixed beam, let us start. This is a fixed beam. It is fixed at both the ends and there is a load of W1 and W2 here. So at a section X, which is at a distance of X from this support, I have to calculate the bending moment Mx. That will be Mx free bending moment diagram plus Mx bottom sign we can say. So this fixed beam I can also visualize like this. There is a simpler supported beam having a reactive moment of MA and MB like this one. So now consider both the portions separately. One is this without these reacting moments and one is with this reacting moment after removing this external load. So this plus this is equal to this one. So I am considering my fixed beam like this. One is simply supported and in the second case, after removing the external load and applying the reacting moments, if I add both together, I will get this fixed beam. The effect of fixed T will be this way. So this is the effect of fixed T. If I draw the bending moment diagram, then for simply supported beam, my bending moment will be like this. There is a reaction VA and VB. For simply supported, it is small VA and small b. So bending moment diagram will be something like this. Suppose this W2 is greater than this W1, then it will be like this. So this is my free bending moment diagram and fixed bending moment diagram will be like this. This M2, suppose this MB is greater than here. So it will be of trapezoidal shape and having a hogging in the nature. This is sagging and this one is hogging. This is the fixed bending moment diagram. If I superimpose both the diagram, then this is hogging, this one is sagging. So I will get this diagram. This is the resultant bending moment diagram. Now suppose this MB is greater than MA. If this is greater than MA, then the net effect, what does it mean? That bending moment here is more. So the resultant couple will be in this way. So my reaction will be downward. This V will be downward. For simply supported beam, it will be upward at both the ends. So reaction at this end will be, since this VA, small VA is upward and this is downward, so this VA minus V, this will be the final reaction at this VA, and I am considering MB is greater than MA. This is upward, this one is also upward, simply supported beam, and this is for fixed beam. So this reaction, final reaction at VB will be this VB small b plus this VB. This way I will get the final reaction at this end. Now reaction at this end will be MA minus MB upon L. So this is MB, this one is MA. So RA and RB is yes, this RA is V. So I am considering this. This one is V, and this one also will be equal to V. Since no external load is acting, so same reaction will be here. This one is downward, so this will be upward. So reaction at both the ends will be equal. Since this MB is greater than this, so it means my net couple will be more here. So to counteract this reaction will be like this. So this reaction will be downwards. So if I take moment at this end, so it will be V into L. So this is L. This will be Hogging, and this is also Hogging. Oh, both will be negative. VA into L. This is Hogging, and this is also Hogging, is equal to MB. So if I take MB in this way, so it will be MB minus MA, and V into L. I'm taking here, so it will be V into L. So V will be MB minus MA upon L. So this will be reaction here. So V is equal to MB minus MA into L. So this will be downward at A, and the reaction at B will be same, but that will be upward. So these reactions are only due to fixing moments. So final reactions at A, this capital VA, this will be this minus this. Since it is upward, this is downward. So VA due to simply supported beam, and this capital V is due to reactive moments. So this minus this will be the final reactions here, and in this case both the reactions are in the same upward direction. So the final reaction VB is equal to this small VB plus this V. So these are my reactions. Now the actual bending moment at any section will be this mx minus mx dash. This is due to free bending, and this one is due to fixed bending moment. So net bending moment at any section x here will be due to simply supported and due to fixing. So net effect, this bending moment will be mx. Suppose this mx is due to free bending, and this mx dash is due to fix. So this is MA MB. So at this x section, this is my mx dash. Mx dash is so bending moment at this x, this will be this plus this. Mx is the bending moment at this point. This will be this mx due to simply supported plus this mx dash, or we can say this is hogging. So this will be mx plus minus mx dash. I will say mx minus mx dash. So this will be the net bending moment. So since this is a differential equation for curvature, ei into second derivative with respect to x is equal to minus m. So minus m is at mx, it is mx minus mx dash. It will be minus mx plus mx dash. If I integrate it, I will get ei into dy upon dx, and this one if I integrate it, so I will get mx into dx integration from 0 to L. So I am integrating from this is, so this is x 0, x is L here. So total length is L. So I am integrating from here to another end. So this will be 0 to L and this is 0 to L. I am integrating both. Now at x is equal to 0, my dy upon dx is slope. So at x is equal to 0 means x is 0 here. My slope is 0. Since no rotation is there, this line is tangential to this. So my theta is 0. My dy upon dx is equal to 0 at this end. At x is equal to L, when this x becomes this L, my dy upon dx, my rotation at this end is also equal to 0. So now this one will become 0. This one will become 0 here. After putting this dy upon dx is equal to 0. And this mx into dx, what is this? This mx into this dx. This one is mx. Suppose if I consider a small strip of length dx, and this is a very small, so I can take this constant. So this area will be mx into dx. So this will be the area of the bending moment diagram for this portion. If I integrate it from x is equal to 0 to x is equal to L, so what I will get? I will get the area of the free bending moment diagram from here to here. Similarly, for fixed moments, this is mx dash. If I consider it small strip dx, so this one will be mx dash into dx, and if I integrate it from x is equal to 0 to x is equal to L, so I will get the area of the fixed bending moment diagram. So this way I will say this mx dx, this one is the area of the free bending moment diagram. If I denote it by small a, and this one is the area of the fixed bending moment diagram, a dash. So by putting in this equation at x is equal to 0, this one is 0 is equal to, this is the minus area of the free bending moment diagram plus this is area of the fixed bending moment diagram. So what does it means? The area of the free bending moment diagram is equal to area of the fixed bending moment diagram. Means whatever is the area of the this area of the free bending moment diagram, so whatever will be the area of this free bending moment diagram, same will be the area of this fixed bending moment diagram. Suppose this is 250 mm square area of this one. So area of this will also be 250 mm square. So area of the fixed bending moment diagram is equal to area of the fixed bending moment diagram. So this is one conclusion. Oh, mistakenly I has area of the free bending moment diagram is equal to area of the fixed bending. Now as we know, this EI into second derivative with respect to x square is equal to, this was my equation. If I multiplied it both the ends by x, if I multiply this and this also by x, I will get m minus mx into x plus mx dash into s. Then if I integrate this, then integration of this and integration of this from 0 to L. 0 to L means from this end to this. So this is mx into dx. Mx into dx, this is the area, and if I multiplied this area with this distance, mx into dx into x, so I will get, this is the area moment of this area about this end, and this is the distance of the centroid of this area from this one. If I integrate it from 0 to L, similarly mx dash into dx, this is the area of this strip, and if I multiply this distance, I will get the moment of this area about this ends. If I integrate it from 0 to L, this also from 0 to L, what I will get? I will get area of this free bending moment diagram, suppose this is A, into x bar. X bar is centroid of this portion, suppose this is G, and this will be the centroidal distance from this point. So I will get x bar, distance of the centroid of this from this one. Similarly, area of this, if I integrate it, mx dx from 0 to L, so mx dx is the area and multiplied by this one. If I integrate from this, then I will get area of the first bending moment diagram and its centroidal distance. Suppose this is this, so I will get this one. So this is where we were. I have multiplied both the ends by x, and then further I have integrated it. So I will get integration of this portion will be this one. Integration of will be x into integration of d square y on dx square minus derivative of this one and integration of this one. So this will be 1, and derivative dy upon dx square, this will be y. So x into integration of dy upon dx. Oh, this is the So x into dy upon dx minus y. This is what I will get is equal to, this is the area of the fixed bending free bending moment diagram and its centroidal distance plus this one, area of the fixed bending moment diagram with its centroidal distance, and x bar is the distance of the centroid of the free bending moment, and x bar dash is equal to distance of the centroid of the fixed bending moment diagram. Now at x is equal to 0, my deflection y is equal to 0 and slope is also equal to 0. At x is equal to 0, in this case, when x is equal to 0, my deflection y is equal to 0 and my slope is also equal to 0. When x is equal to L, means at this end, my deflection is 0 and the rotation is also equal to 0. Putting in the equations above, so this was the equation. If I put x is equal to 0, y is also equal to 0, means this whole is equal to 0. So 0 is equal to this plus this. So this will become equal to each other. Since area of the free bending moment diagram A is equal to A dash, this is the area of the free bending moment diagram, this is area of the fixed bending moment diagram. So both will cancel. So x bar is equal to x dash bar. Means what is this? This is the central distance. This x bar is the centroidal distance of free bending moment diagram, and this is central distance of fixed bending moment diagram. So x bar is equal to x dash bar, means distance of the centroid of the free bending moment diagram from the spot A is equal to distance of the centroid of the fixed bending moment diagram from A. So from this derivation, what we have get? One is area of the free bending moment diagram is equal to area of the fixed bending moment diagram. This area is A, this is A dash. So area of this is equal to area of this. Secondly, its centroidal distance. Suppose this is centroid, this distance, this central distance from this A spot is equal to the central distance from this. Means whatever will be the central distance of the free bending moment diagram, that will be equal to the same central distance of the fixed bending moment diagram from the same end. So this become equal to this. Secondly, area of the free BMD is equal to area of the fixed bending moment diagram. So these are the two conclusions which we have arrived in the derivation of this. Now let us start some few cases. So there is a case of a fixed beam and having a central distance W here. So I can consider it in both way. This is equal to simply supported beam due to external load and the reacting moments. So I am considering separately. So this is simply supported. This is the effect of the fixed T. The free bending diagram of the simply supported beam will be this one, and WL/4 will be the reaction here. So W/2 is the reactions. So it is WL/4. And in case of fixed bending, fixed end moments, this is MA, this is MB. Since this beam is symmetrical, so there is a central load W and distance is also equal. It means my fixing moment MA and MB are also equal to each other. So this will be a triangle, rectangular. So this is a rectangle. My fixed BMD. This is free BMD. If I superimpose both, then I will get this one. I will get this. This is the final bending moment diagram. So area of the free bending moment diagram is the area of the fixed bending moment diagram. Area of this is equal to area of this. So area of this one is equal to 1/2. This is WL/4 into this. And area of fixed bending moment, this is a rectangle. So this will be MA into L. So MA is equal to WL upon 8. It means WL upon 8 is the fixed end moments here. So this will be WL/8. And similarly, if this is W/8, this one is also equal to WL/8. As the beam is symmetrical, there is a central load and the distance is same. So it means reactive moments will be same. This is WL/8 and this is W/8. Reaction will also be equal to each other. If this is W, this will be W/2 and W/2. So same reaction, as the moment are also same. So W/2 and W/2 same reactions. So it means, so there are 2 points of contrafluxure. One is this and second is this one. And the distance will be if this is L/2, so this will be L/4 from both the ends. So L/4 from the ends. Now if I want to find the slope and deflection, then this is my double integration method. EI into second derivative with respect to x square is equal to minus m, and m is the moment at so I calculated this is WL/8 fixed ending moments at both the ends, and the reaction is half of this load. So at any distance x from this force, my moment will be W/2 into this distance. This will be mx due to free bending moment plus mx dash due to fixed. So now moment at this will be W/2 into this x. This is sagging minus this one. This is WL by 8 is the fixed moments and hogging in nature, and so this will be my bending moment at distance x from this force. So this will be W by 2 into x plus WL by 8. This I will get. If I integrate, then it will be EI into dy upon dx. This one minus W by 2 x square by 2 plus WL by 8 into x plus coefficient C1. Now at x is equal to 0, it means my slope is 0. Dy upon dx is equal to 0. So if I have put x is equal to 0 here, 0, this 0 plus 0, so C1 is equal to 0. So EI into dy upon dx will be minus W by 4 x square plus WL by 8 into x plus this becomes 0. So this is my slope equation. If I integrate it further, I will get EI into y minus WX cube upon 4 into 3, 12 plus WL by 8 into x square by 2 plus coefficient C2. Now at x is equal to 0, my y deflection is 0. X is equal to 0, my deflection is also equal to 0. So if I put the value x is equal to 0 here, y is equal to 0. So C2 will become 0. So putting the value of C2 in this equation, I will get EI into y is equal to minus W by 2 x cube plus WL by 8 into x square. So this will be my deflection equation. So in this case also, my maximum deflection will be at the center. At the center, due to symmetry, my maximum deflection will be at the center when x is equal to L by 2. Half of this total length, when x becomes equal to L by 2, then I will get maximum deflection here. So this is the deflection equation. If I put x is equal to L by 2, I will get maximum deflection that will occur at the mid-span center. So if I put x is equal to L2, I will get EI into y max. This will be W upon 12 into L by 2 cube plus WL by 8 into 1 by 2 into L by 2 squares. I have put the value of x is equal to L by 2 in these equations. So I will get this one minus WL cube upon 96 plus WL cube upon 64. So LCM of this will be 192 minus 2 plus 3. So this will be minus 2 plus 3 is equal to 1. So it means yx is equal to WL cube upon 192 EI. So WL cube upon 192 EI. So this is the deflection, and this will be equal to 1 by 4th of the deflection of a simply supported beam. Suppose had my ends were not fixed, as in the simply supported beam, my deflection at the center will be WL cube upon 48 EI. But due to fixed ends, my deflection get reduced here. So in this case, this will be my deflection, which is equal to this one, WL cube upon 192 EI. If I compare this and this, then it will be 1 by 4th of this one. If I multiply this by 4, means this is the deflection of fixed, and deflection of simply supported is, So this is WL cube upon 192 EI divided by this one. So I will get 1 by 4. Means in case of fixed beam, this will be 1 by 4 of simply supported. So there is a reduction of 3 by 4th. The deflection get reduced by 3/4. So 1/4 will be the net deflection in case of fixed beam. Now let's start the case number 2. If the load is UDL, then free bending moment diagram will be this one. This is WL square by 8. And as in this case also, my beam is symmetrical. So fixed moment MA and MB will equal to each other. So this is my fixed BMD. Now if I as we know, area of this is equal to area of this. Area of the free BMD is equal to area of the fixed. So area of this free BMD will be, this is a parabolic. So area of this will become 2 by 3 of this ordinate, which is WL square by 8 into this length. The area of the free bending moment diagram, and area of this fixed beam, this is a rectangle, MA is equal to MB. So this is MA into this length. So it will be WL square upon 12. So WL square upon 12 is the fixed end moment in case of simply supported beam. This will be WL square by 12, and this will also be same. If I superimpose both the diagram, then I will get final bending moment diagram. This one is free bending moment diagram, and this is my fixed bending moment diagram. I have clubbed both together. I have superimposed both. Then I will get this one. This is Hogging here, and this one will be Sagging. This is WL square by 2 Hogging. At the center, since this total deflection is, this ordinate is WL square by 8 minus this one, which is equal to WL square by 12. So I will get so this is WL square upon 24. So WL square upon 24 will be this one. So this ordinate is WL square upon 24. And there will be 2 points of contraflexure. One is this and one is this one. So this is what I have explained. Area of the free bending is equal to area of the fixed. With this I will get MA MB is equal to this one. Now at any distance from the A, this I have calculated, this is WL square by 12. Both the fixed and moments are WL square by 12, and the reaction at this will also be equal to each other. So this is a WL is the total load. So total load is equal to, this is per unit run. So W into L is the total load divided by 2. I will get reaction. WL by 2, WL by 2. Now at any section x, which is x distance from here, bending moment will be mx free plus mx fixed. Since one is sagging and other is hogging, so this plus and this is minus. So at any distance, mx will be this minus this, and this will be, if I take moment at this, so it will be WL by 2, this is the reaction, into this distance, minus this is hogging, so this will be WL square upon 12, and due to this UDL, this will also be equal to WL square upon 2, this will also be hogging. So this will be the net bending moment at x, WL by 2 into x minus 12 minus WX square by 2. So for finding the point of contraflexure is equal to where my moments mx becomes 0. So if I put mx is equal to 0, then this equation becomes equal to 0. So this will be, this is a quadratic equation, x square minus lx plus l square by 6 is equal to 0. So with this I will get x is equal to L by 2 plus minus L by 2 into root 3. So there will be 2 points of contraflexures will occur and are equidistant from the center of the span. So each point of contraflexure is at a distance of L upon 2 root 3 from the center of the span. So x is equal to L by 2 plus L upon 2 root 3, and L, this x, L by 2 minus L upon, this L by 2 is, what is this? L by 2 is the, this distance is L by 2. If I add this L upon 2 root 3, if I add this one, I will get so this one is L by 2. If I add L by 2, this one is L by 2, means this distance. If I add L by 2 plus, if I add this one in L by 2, so I will get this. If I subtract this one from L by 2, I will get this. It means this point and this, both the point of contraflexure are equidistant from the center. So this will be L upon 2 root 3, L upon 2 under root 3. So this distance is same from the center. So 2 points of contraflexure will occur and are equidistant from the center of the span. Each point of contraflexure is at a distance of L upon 2 root 3 from the center of the span. So from this center of the span, both the point of contraflexure are equidistant, and the distance is L upon 2 root 3 and this one. If I take minus, I will get this point. If I choose plus, then I will get this point. Suppose if I want to know the slope and deflection, then bending moment at any section is equal to, this is my differential equation. EI, second derivative of y with respect to x square, is equal to minus m. And what is minus m? This is WL square upon 12. This reaction is W, total load W into L will be shared by both the reactions, WL by 2. Now at any point, what will be the value of my m? This is WL by 2 into this x distance minus this one minus this. So if I put the value of this here, minus WL by 2 into x minus this one. Now take it outside. So this will be minus WL by 2 into x plus WL by square 12 plus this is WX square by 2. If I integrate, then I will get EI into dy upon dx is equal to minus WL by 2 into x square by 2 plus WL square by 12 into x plus WX cube upon 6 plus coefficient C1. Now when x is equal to 0 means at this end my slope is 0. So I will get C1. So C1 is equal to 0. C1 is equal to 0. If I get the value of C1 in this equation, I will get this. So this one is the slope equation. If I integrate it further, I will get EI into y minus WL by 4 into x cube upon 3 plus WL square upon 12 into x square by 2 plus W by 6 into x4 upon 4 plus C2. At x is equal to 0 means here at x is equal to 0, my deflection y is also equal to 0. So if I put x is equal to 0, this y is also equal to 0 means C2 is equal to 0. Now putting the value of C2 in this equation, I will get this one. So now this is my deflection equations. Of course, in this case also maximum deflection will be at the center due to symmetry. Maximum deflection will be here at the center. So when x becomes equal to L by 2 means half of this span, I will get deflection here, which will be maximum deflections. So this is my maximum deflections. So maximum deflection will occur at the center when x is equal to L by 2. If I put the value of L by 2 in this equation, then I will get EI into y max. This y becomes y max. WL upon 2L, I have put this simply x is equal to L by 2 in this equation. So I will get finally this one, WL by 4 divided by 384. So what is this? In case of simply supported beam carrying UDL, my maximum deflection will be at the center, and this will be pi upon 384 WL4 upon EI. In case of fixed beam carrying the same UDL, my deflection will be, this is y max and this we calculate to this what I have calculated. It means in this deflection is 5 times of this equation. So deflection of the fixed beam divided by deflection of the simply supported beam, then this will be 1/5. So this deflection is 1/5. In case of simply fixed beam carrying point load, this is 1/4, and if it carries UDL, then the maximum deflection will be 1/5 of the simply supported beam carrying UDL. So it is 1/5 of the central deflection of the simply supported beam. Now let's take the another case. There is a fixed beam and there is a W load which is acting eccentrically. Means this is not at the center. This is acting somewhere here. The distance from this end A, small a, this one is B. If I draw the free bending moment diagram, this will be W into AB upon L, as we know. If I take moment at this, then R1 into L is equal to W into B. So this reaction will be WB upon L. If I take moment at this point, so this will be WB upon L, this reaction into this distance. I will get WAB upon L. This one, W into AB upon L. This is the maximum bending moment, of course, at the point, and fixed bending moment is like this. So this load is closer to this spot, so obviously maximum bending moment will be here at this spot. So MB will be greater than this MA. This is my fixed bending moment diagram. If I superimpose both, then I will get final bending moment diagram. Now, as we know, there are two things. One is the area of the free bending moment diagram is equal to area of the fixed bending moment diagram. One condition is this. So area of this will be area of free BMD is equal to area of fixed BMD. Area of this will be 1/2 into this ordinate WAB upon L into this length. And the area of this is a trapezoidal. So area of this will be MA plus this MB upon L into MA plus MB by 2 into this distance. So with this I will get one equation. So that will be MA plus MB is equal to WAB upon L. This is L. So this is equation number 1. Now second thing is this. The central distance of the free BMD window from this sports, if I consider this sports, so this x bar central distance of this area from this spot is equal to central distance of this fixed BMD from this force. This is x dash. Both are equal to E. Equal. Now this is x bar is equal to central distance of this triangle, and this central distance x bar is equal to, obviously, this is A, this one is B. So this L plus A divided by 3, this will be the central distance. So this central distance, this one is equal to L plus this distance A, L plus this divided by 3. This will be x. Now central distance of this from this, suppose this is x dash bar, this will be, what is the formula for central distance for trapezoidal? This is MA plus 2 times of MB MA plus 2 times of divided by MA plus MB into 1 by 3 of this distance. So I will get this one. Now this is equal to this. So I will get, so after following this equation, I will get this equation. Now MA plus 2 MB is equal to L plus A into MA plus MB into this L, and so this is equation number 2. MA plus 2 MB is equal to this one. And what is equation number 1? MA plus MB is equal to, equation number 1 is MA plus MB is equal to WAB upon L. So if I put MA plus 2 MB is equal to L plus A, and this is WAB upon L. So there are two equations, one is this, another is this one. So after putting, I will get this equation. This is WAB upon L. MA upon MB is equal to WAB upon L. So this will be WAB upon L square. And second equation is MA plus MB is equal to WAB upon now if I subtract both, then I will get minus MB is equal to this. If I subtract, then I will get this L plus A into WAB upon L square minus this one, and this will be equal to, so minus MB is equal to this one. So after solving this, I will get MB. MB is equal to WA square B upon L square. If I put the value for MB in any of the equation, since MA upon plus MB is equal to WAB upon L, this was my first equations. If I put the value of MB in this equation, I will get MA, and MA will be this one, and this L minus A if I subtract this A from this L, so L minus A is equal to this one, which is equal to B. So it means this will be W A into B square upon L square. It means, so these are my fixed end moments carrying eccentric load. So this moment is equal to W into this distance into square of this next distance upon L square. Similarly, this moment is equal to W into this distance into square of the this next section length upon L square. So this way, this is my MA fixed end moment at this end, and this is MB, W B into A square. Means this is W into this distance into square of this one upon L square. Similarly, W into this distance into square of the next length upon L square. So these are my fixed end moments. Now let us take another case. There is a fixed beam carrying UDL not for the whole length but for a distance A. This distance is A from this spot, and I have to calculate the fixed end moments at A and B. So what we can do in this case is very simple. I will consider first a small stretch dx. So let us consider this one. So W into this distance will be the load. Consider it as a point load in place of UDL. Since this length is very small, I can consider this W into this is a point load, and due to this W into dx small load, there will be my fixed end moment. Suppose this is DMA and this is DMB. So this is fixed end moment due to this small elementary load DMA, and this will be equal to formula as we have. This DMA means fixed end moment diagram. Due to this load, this is W into dx is the load into this distance into square of this one. This is L minus upon this distance square, and this DMB will be, this is the point load into this length into square of this one upon L square. So these are the fixed end moment due to this small elementary load. If I integrate it from x is equal to 0 to x is equal to A. If I integrate it from x is equal to 0 to x is equal to A, I will get the fixed end moment at A and B. This is due to this small elementary load, and if I integrate it from x is equal to 0 to x is equal to A, I will get MA and MB. So total fixing moment at A is equal to integration from x is 0 to A, means here to here. So I will get W upon L square into x into Lx minus square dx. This will be x square, x into L square plus x square minus 2Lx. This one. Now, integration of this is L square x plus x cube minus 2L x square dx. And this will be W upon L square. L square into x square by 2 plus x 4 upon 4 minus 2L x cube upon 2. Now, putting the value of x is equal to a, I will get this one. Now, finally, I will get this. So, this is my formula for UDL not carrying the whole span. For this one. So, this is L minus A, this is A. So, due to this UDL which is not covering the whole span, the moment at this end, fixed end moment, so MA is equal to W A square upon L square into 6L square plus 3A square minus 8LA upon 12. So, this will become my formula WA square upon 12L square 6L square plus 3A square minus 8LA. So, this way I can calculate. So, this will be my MA. Similarly, total fixing moment at B, this will be the integration of DMB. So, this DMB was this. So, this is integration from 0 to A will be equal to the integration of this will be Wx square upon L square into L minus x into dx. So, this W upon L square and integration from 0 to A is equal to x square into L minus this is L square L minus x cube. So, further W upon L square into x, this L into x cube upon 4 minus 4 upon 4. So, finally, I will get this WA cube upon L square is equal to 4L minus 3A upon 12. So, this is the formula WA cube upon 12L square into 4L minus 3A. So, with this I can calculate the fixed moment at A and B. Means if there is a fixed beam carrying UDL for this portion, so this moment will be equal to WA cube upon 12L square, this is L, into 4 times of this L minus 3 times of this A, and this MB will be equal to MA is equal to WA square upon 12L square into 6L square plus 3A square minus 8LA. So, MA is equal to this one, MB is equal to this one. So, this formula needs to be recalled regularly. So case fifth is, suppose that there is a fixed beam. So this is a fixed beam and it carries a triangular load. So this is the triangular load. Its intensity varies from 0 to W at the another end. So now to calculate the fixed end moments, we can consider a small strip. The intensity is W here. So at this point, which is x distance from this A, so this will be W and into this upon this L is equal to this distance x, this one upon x. It means Wx upon L is the load intensity at this point. So consider a small strip of dx. So this will be intensity is W upon L into x into this distance dx. So I will get this point loads. I can consider this as a point load. This is W upon L into x into dx. So this is x, this will be L minus x. So fixed end moment due to this small elementary load will be dma, this is dmb. So dma is equal to how much? This will be, as we know, this is the load I can into this distance into square of this upon L square, and dmb will be equal to this load into this distance into square of this upon L square. So this is because of this small elementary load. If I integrate both from x is equal to 0 to x is equal to L, I will get MA and MB. This is DMA, DMA. So total fixing moment at A, I integrated this from 0 to L, and this will be WL square upon 30. Similarly, MB, if I integrate this, I will get WL square upon 20. What does it mean? If there is a fixed beam carrying a triangular load whose intensity varies from 0 to W here, then my this moment is equal to WL square upon 30, and this moment is equal to WL square upon 20. So this is MB and this is a MA. Now same case, suppose this triangular load is not covering the whole span. This is covering a distance A from this force, this one. So this is the case, and I have to know the fixed end moment MA and MB. So same, in this intensity is W here. I consider distance x. So this intensity will be, I have to calculate first this intensity. These are two similar triangles. So this W upon this length is equal to this intensity divided by this length. So this will be, this is this W upon A. So this is A. This will be W upon A into X. So W upon A into X is the intensity here. Now consider this as a small elementary loads. W upon A into X is the intensity multiplied by this distance dx. I will get this one. Consider this as a point load, and fixed end moment because of this small load is equal to W upon A into X into dx. This is the load into this distance into square of this distance upon L square. This dmb is equal to this load into this distance into square of this one upon L square. So these fixed end moments are because of this small elementary load. If I integrate from x is equal to 0 to x is equal to a, I will get this MA and MB. So this is DMA, DMB. So integrate from 0 to L, A. So finally, I will get this one. WA square upon L square. This is L square, don't get confused. WA square upon L square into 10L square plus 6A square minus 15LA upon 30. So this will be the MA. And similarly, by integrating this DMB, I will get MB. So MB is equal to WA cube upon 20L square into 5L minus 4A. This is MA and MB. So MA is equal to this one, MB is equal to this. So this is the case when triangular load carrying a distance A from this spot. This is L. So this moment MA and this moment MB. So MA, this MA is equal to this one, W into A square upon 30L square into 10L square minus 15LA plus 6A square. MB is equal to WA cube upon 20L square into 5L minus 4A. Now, when this A becomes equal to this length, when this A becomes equal to this, means when the load intensity covers the whole span, when X, this A becomes equal to L, means this. So in this case, if I put the L is equal to A in this equation, so I will get 10L square minus 15L square plus 6L square. This 16L square minus 15L square means L square. So I will get WL square upon 30, the same which we have derived earlier, WL square upon 30, and this will be WL square upon 20. If I put this one, so this will be 5L minus 4L this L, W, WL square upon 20. I will get this one. When A is equal to L by 2, means when this load intensity covers the half portion. This is L, and when this distance is half of this one, then by putting A is equal to, this was a L by 2 in the above equations, I will get MA is equal to, this is W, this will be L by 2 square upon 30L square into 10L square minus 15L, A is L by 2 plus 6L square by 4. So I will get B is equal to MA. So L by 2 square 30L square, putting A is equal to L by 2 10L square minus 15L by 2 plus 6L square. So this will be L by 2 square upon 4 into 30 L square. This will be LCM is 4, so it will be 40L square minus 30L square plus 6L square upon 4, WL square upon this will be 40 minus 10 plus 6, 16L square by 4, and this will be 120. So this is, so WL square upon 30, MA is equal to WL square upon 30, and MB is equal to WL cube upon 20L square into 5L minus 4L. So this will be WL by 2 cube upon 20L square into 5L minus 4A. And 4A is equal to L by 2. So this will be WL cube upon 8 into 20L square into 3L. So this will be 3 upon 160 WL square. So this is my MB. So MA is equal to this one, MB is equal to this one. So it means when this triangular load covers half of the portion. So this is what the case when this triangular load, when this A becomes equal to half of this length, this is L, L by 2 and L by 2. So when this A becomes half of this, then my fixed net moment at this end will be WL square upon 30 and MB will be 3 upon 160 WL square. This one. So this is the case. Now suppose this is the new case. This triangle load covers in this way. Load intensity varies from 0 to maximum at the center like this. So this is the case. So this can be visualized as a this portion and this portion. So this is equal to this plus this. So I have taken separately the half portion and half portion. If I club both together, I will get this ones. So I am considering like this way. So this is equal to this plus this one. Now fixed end moment, because of this, as we have calculated, this is WL square upon 30 and this will be WL L square upon 160 into 3. If I reverse this way, then this fixed end moment will becomes this one 3 upon 160 WL square and this will become WL square upon 30. If I add both together, this will be WL square upon 30 plus 3 upon 160 WL square. I will get total this fixed end moment at A and this will be this plus this. And this will be this plus this, means both are equal to each other due to symmetry and otherwise also this plus this. So both will be same. And if I add both, then WL square upon 10 I can take common, 1 upon 3 plus 3 upon 16. It was WL square upon 10 is 48. The LCM 16 plus 9. This will be 25 upon 48. This will be 5 upon 96. 5 upon 96 WL square will be the fixed end moment. So 5 upon 96 WL square and the same will be at this end also 5 upon 96 WL square. It means formula for the fixed end moment in case of a triangular load whose intensity varies from 0 to maximum at the center. Another case is that suppose I have a fixed beam and there is a settlement, there is a sinking, so deflection is there. There is a, this end is settled here, so settlement means sinking. This is delta. There is a settlement of this end from respect to this end, there is a delta. So what will be my fixed end moment because of this settlement, because of this sinking? Similarly, so as we know, so no external load is acting, so my fixed end moment will be same. So MA is equal to MB. Why? Because if I visualize it, I can say my this end is lower to this end by delta. Otherwise, I can say my this end is higher than this end B by delta. So this end is higher than delta, this is lower than delta. So my total fixed end moment will be same, and its deflected shape will be like this way. It will deflect like this way. So radius of curvature will change here. So my fixed end moment MB will be this way. So this will be sagging in nature. Will try to rotate in such a way so that this rotation becomes zero. This tangent becomes along this line, as this was the function of fixed end, and same this will be hogging. So far my both the moments are hogging in nature, but in this case this will be sagging and this will be hogging. And to calculate these fixed end moments, let us proceed. As we know, EI into second derivative is equal to minus x, and suppose a reaction is, let us assume a reaction is V. Since no external load is acting, so my reaction will also be same. If this is upward, this will be downward. So let us assume this is upward V. Now bending moment at any section, this will be V into this x minus this m, which is same. So Vx minus m. So EI into second derivative with respect to x square is equal to minus m. So this will be minus Vx minus this one. So this will be minus Vx plus m. If I integrate it, then I will get EI into dy upon dx square minus Vx square by 2 plus mx plus c. When x is equal to 0, means this x is equal to 0 means here my slope is 0, this rotation is 0. So if I put 0, then 0 0 c1 is equal to 0. It means my slope equation is this: I into dy upon dx is equal to minus Vx square plus mx. I will get this one. So now this is my slope equation. Let's assume this is equation number 1, and x is equal to L. When then this x becomes L equal to L, at this point also my slope is 0. So when x is equal to L, dy upon dx is equal to 0. So if I put this 0, this is VL square upon 2 plus ML. So I will get 0 is equal to minus VL upon 2 plus M, or I can say M is equal to VL upon 2, means my fixed end moment is equal to reaction into L by 2. So this is 1. If I integrate it further, then I will get EI into Y is equal to minus Vx cube upon 6 plus mx square plus C2. As we know, at x is equal to 0, means when this x is equal to 0 at this point, my y is equal to 0. When x is equal to y is equal to 0, if I put 0, 0, 0, so C2 is equal to 0. C2 is equal to 0. So if I put the value of C2 in this equation, I will get this EI into y is equal to minus bx cube upon 6 plus mx square plus 2. So this is my deflection equation. So this is the deflection equation. When x is equal to L, when x is equal to L, means at this point my deflection is delta. So y is equal to this one. When x becomes equal to L, then y is equal to delta. So putting this value y here, it will be EI into delta is equal to minus VL cube upon 6 plus ML square by 2. So this one, and as we know V is equal to 2m upon L. So by putting the value of V in this equation, EI delta is equal to ML square by 2 into L minus L cube upon 6 into V 2m upon L. I will get ML square by 2 is minus ML square upon 3. So I will get this one. And M is equal to 6 EI delta upon L square. So this will be my formula for fixed end moment. It means when there is a settlement of delta, my this moment will be 6 EI delta upon L square, and this will also be same. This is sagging here and this one is hogging. Now reaction as we know, reaction V is equal to 2m upon L. By putting the value of m in this, I will get 2 upon L into 6 EI delta upon L square, means V is equal to 12 EI delta upon L cube. It means my shear force at A is equal to this one, reactions. So my this reaction is 12 EI delta so this moment is 6 EI delta upon L square. This one is also equal to 6 EI delta upon L square, and this reaction, this will be downward 12 EI delta upon L cube, and so this will be upward. This will be upward. Why this will be upward? Because if I take this reaction R into this L, this is sagging and this one is hogging, and this one is sagging, means plus. So this R into L is equal to, this will becomes plus, so this will be 12 EI delta upon L square, this L cube. So 12 EI delta upon L cube upward, and this will be downward, 12 EI delta upon L cube. So shear force at A is equal to positive, this one, and it will be negative here. Second case is that when there is a couple, so there is a couple moment which is acting at this point, which is at a distance of A from this end and B from this one. So this one is the case. So for finding the fixed end moment, what I can do, I am treating this as a couple. So this is a couple of load. Suppose W is the load, like this, and delta A is the lever arm. This is the perpendicular distance, lever arm is delta A. Suppose this distance is delta A, this one is A, and this I can treat is delta A. This is W, the load. Now the effect of this will be couple. So this load into this lever arm, W into delta, I can say that my M is equal to W into delta E. So I am treating this couple easy to this W into delta A. Now fixed end moment because of this will be how much? So this one will be, it will rotate in this way. The effect of the couple will be, there will be sagging in this portion. So it will rotate in this way. So it will try to create sagging in this portion, and there will be a hogging here, like this way. Try to rotate in this way. It means this is a sagging moment and this one is a hogging. So now this moment at A, this will be, if I consider this load, then effect of this will be like this, and effect of this load will be like this one. So if I treat this as minus, this is acting upward, this will be W into this distance into square of this one. This is A, so this will be L minus A upon L square, and because of this load it will be plus W into this distance, which is A plus delta A, into square of this one. This will be L minus this distance upon L square. I will get MA. So MA is equal to this one. So it will becomes WA upon L square into L minus A square. I can take it this way, and this on the right hand side. So ignoring the product of this delta is very small, so I can consider a square of this 0. So then WA into L minus A square upon L square is equal to minus W A upon delta A plus delta A into, this will be L minus A square plus delta A square minus 2 times of L minus A into delta A. So finally I will get this one. The moment is this equal to M 0 into B into 3A minus L upon L square. Means this is a fixed beam and there is a couple which is acting at a distance of A from this support, and this is L minus A. Suppose if I consider E, then its deflected shape will be like this. So this MA is equal to this moment, suppose this is M0 into this distance into 3 times of this minus L upon L square. This will be the formula. This couple into this distance, next distance into 3 times of this distance minus L upon L square. Similarly, MB is equal to the couple M0 into this distance into 3 times of this distance minus L upon L square. So this way you can remember the formula. So this is the case. Now, effect of rotation of a support. Suppose my ends, this end is not fully fixed. There is some kind of rotation is there. So we have considered the effect of settlement, sinking. Let us say some rotation is permissible. So I will say this beam, this end is not perfectly fixed. This is partially fixed. This end is fully fixed. So there is some rotation of del theta. There is a theta b, some rotations. So suppose some rotation is there, means I have applied a moment at this end. Because of this moment, some rotation is there. This is theta b. So because of this rotation, what will be my fixed end moment here? This MA. So same, I can consider it so this is MA. If I take moment here at B, it will be, let us assume this reaction is RA, this is RB. So RA into this distance, this sagging minus MA is equal to, this one is hogging. So this is also minus MB. So RA will be equal to MA minus MB upon L. So this will be my reactions. If I think minus this hogging. This is sagging, means this is sagging. So RA into L, this is sagging, and this one is hogging. Hogging means negative, sagging positive, hogging negative. So this is the sign convention which I follow. The same you people can follow. So RA into this L minus this MA is equal to, this is sagging, means positive MB. So RA will be is equal to MA, this will become plus MA plus MB upon L. This way I will get reactions. So this RA is equal to MA plus MB upon L. If I take a section X, hence moment at this will be MA plus MB by L into X. So RA into X minus this MA. So this will be MA plus MB by L into X minus MA. So this will be my MX at this point, bending moment. Now, as we know, EI into second derivative with respect to x square is equal to minus MX. So minus MX is equal to RA into X minus this. So this will be minus, putting the value of RA minus L, I will get these equations. As we know, integrate it further, I will get minus MA plus MB x square by 2 plus MAX into this one. As we know, at x is equal to 0, x is equal to 0 means at this point, my dy upon dx, my slope is 0. So when x is equal to 0, dy upon dx is equal to 0, putting the value x is equal to 0, I will get C1. C1 is equal to 0. It means putting the value of C1 in this equation, I will get EI dy upon dx minus MA plus MB x square by 2 plus. This is my slope equation. This is the slope equation. If I integrate it further, I will get this one. X cube upon 6 plus MA x square by 2 plus C2. At x is equal to 0, my deflection is also equal to 0. When x is equal to 0, this deflection is 0. Y is equal to 0. By putting the value x is equal to 0, y is equal to 0, I will get C2. C2 will also become equal to 0. Then my deflection equation becomes minus MA plus MB into x cube by upon 6 plus MA x square by 2. So this is my deflection equation. When x is equal to L, my deflection is also equal to 0. Means when x becomes equal to L, deflection at this is equal to 0. Means putting the value x is equal to L in this equation and putting y is equal to 0, I will get this one. So this will be my equations. So finally I will get one equations which is 0 is equal to 2MA minus MB is equal to 0. This is my one equations. When x is equal to L, my slope equation is this one. This was my slope equation. If I put x is equal to L in this equation, what I will get? I will get this dy upon dx is equal to theta b. Slope at b. When this x becomes equal to L, then my rotation is theta b. Dy upon dx is no 0 here. It is theta b. And since the rotation is anti-clockwise, I will treat this theta b as negative. So when x is equal to 0, my slope is minus theta b, and putting the x is equal to L in the slope equation, in this equation, I will get this one. So this will be my another equations. MA minus MB is equal to minus 2 EI theta upon L. So this is my another equations. So first equation was 2MA minus MB is equal to 0. It means MB is equal to 2MA. So by putting the value of MB is equal to 2MA in this equation, I will get this minus 2 EI theta upon L is equal to MA minus 2MA. Means minus MA, minus minus plus. So MA is equal to 2 EI theta upon L. So this will be my fixed end moment. at A, 2ai theta upon L. And what is MB? MB is equal to 2 times of MA. 2 times of MA is equal to 4ei theta upon L. So it means, if suppose I have a fixed beam and this end is not perfectly fixed, this is perfectly fixed. So some rotation is there. Some rotation theta B is there. So because of this rotation theta B, my moment at this will be 4ei theta upon L, and this MA will be half of this, 2ei theta upon L. So this will be 2ei theta upon L. Theta is theta B, I can say theta B. So in case of some rotation not fixed, this is not fixed. So this will be the fixed end moment. And if I want to know the reactions here, then it will be, suppose this is RA, this is RB. By taking moment at this, so RA into this L, this is Hogging, is equal to moment here. And this one is sagging. This is sagging. So RA upon L, this is this plus this, so 6ei theta upon L square. So this will be my reaction upward, and this obviously will be equal to downward. As sigma V is equal to 0, no external load is there. So 1 is upward, this will be downward. So 6ei theta upon L square. These are my reactions. Now, degree of fixity at support to have maximum bending moment as small as possible. In case of fixed beam, both the ends are fixed carrying UDL. The maximum bending moment at the mid span is this one. As we know, so far, this is my fixed beam carrying UDL. So its bending moment, fixed end moment are WL square upon 12. This is WL square upon 12. L square upon 12. This one is also equal to WL square by 12. And this one is WL square upon 24. Means this positive portion from here to here, this is WL square upon 24. So this is the final BMD in case of fixed beam. What he want to know, that how much degree of fixity at support is required to have the maximum bending moment as small as possible. So this is the maximum bending moment, this one and this is. So for the maximum bending moment to be as small as possible. So this is Hogging one, this is Hogging, this is sagging. So maximum Hogging is equal to WL square upon 12, and maximum sagging is this one, WL square upon 24. So for bending moment, maximum Hogging should be equal to maximum sagging. So bending moment to be as maximum as possible, for this Hogging should be equal to this sagging. So in this case, I will say my bending moment is as small, maximum bending moment is as small as possible. For this should be equal to this one. As we know, this total is equal to how much? This is WL square upon 8. WL square upon 8. This is the total ordinate. This is a simply supported beam. Bending moment diagram, this is a fixed one. So this total ordinate from here to here, this is WL square upon 8. For a maximum bending moment to be as small as possible, my this ordinate should be equal to this one. Maximum sagging should be equal to maximum sagging. It means this is equal to this one. Suppose this is A. So this will also become equal to A. So this A plus this A is equal to 2A, and this 2A is equal to WL square by 8. It means A is equal to WL square upon 16. So it means when this becomes WL square upon 60, like this, WL square upon 60, I will say my maximum bending moment is as small as possible. So this, in this case, WL square upon 16, this also becomes equal to WL square by 16. So my this ordinate becomes equal to this. That means what is the function of this fixed end moment? The fixed end moment, the function of fixed end moment so this will deflect like this, and this fixed end moment effect of this will be hogging. So the downward deflection, this is upward deflections. So effect is O. So what is the function of this? They try to rotate this rotation to 0. So it's trying to create a hogging here. So when I reduce this fixed T, so this was the case. This was W L square upon 24. Now, in case my maximum bending moment to be as small as possible, this will be my maximum bending moment diagram. This will be WL square upon 16, and this will also become equal to WL square upon 16. When this becomes equal to this, I will say my maximum bending moment is as small as possible. Means total is WL square by 8. So half of this is equal to this and this one. It means my hogging effect is less here. This is less than this one. So when I reduce the fixed T amount, when I permit some kind of rotation here, like this, if I allow some rotation here, then in this case, my maximum bonding moment will be as small as possible. For this, I have to permit some kind of relaxability here. I have to reduce some kind of fixed T here. And how much degree of fixed T will be there? So, in case of fixed beam, both end of fixed carrying UDL, the maximum bending and the mid span is this one, and at the end is this one. It means the maximum hugging moment is at the end is twice the maximum sagging moment. So this is twice of this one, as this was the case. WL square upon 24. This is WL square upon 12. So this moment is 2 times of this one. So this is twice of this one. It means So if the degree of fixed T at each end is reduced, the hogging moment at each end will decrease, and consequently the sagging moment will increase. If I reduce this degree of fixed T, then this will reduce and this will increase. Means in this case some kind of a rotation is permitted. Some kind of rotation is permitted. So I have reduced the degree of fixity. So hogging will, what is the effect of fixity? Is to create hogging effect. So if I reduce the fixity, then hogging effect will less. Hogging moment will less and sagging will increase. Hence, for the bending moment to be as small as possible, the maximum sagging should be equal to the maximum hogging. This one. So maximum sagging moment should be equal to the maximum hogging moment. Means WL square upon 16. This will also WL square upon 16. WL square upon 16. When this become this, I will say my maximum bending moment is as small as possible. So deflected shape will be like this. So some, I will say some kind of a relaxability is there. So this is not perfectly fixed. Some kind of rotation will be there. Suppose this is theta A, this is theta B. Some rotation is there. So this is theta A, theta B. Some rotation is there. For this I have described. Total maximum bounding is this one. Maximum hogging as these are small. These are 2 times of this. So this WL square upon 16. And rotation will also be same theta due to symmetry. Now the reactions at both the ends will be equal to WL by 2. Total load is W into L by 2. So this will be my reactions. So differential equation will be this one. EI into second derivative with respect to this is minus. So reaction, it will be minus WL by 2 into X. This sagging minus this one, and this moment is equal to this one, WL square upon 16. In this case, for maximum bending moment to be as small as possible, minus this W into X square by 2. So this will be my bending moment at this, and minus of this will be minus W by 2 into X plus WL square upon 16 plus WX square by 2. I will get this one. And this MO is equal to WL square upon 16. So I can put this value straightway here. WL square upon 16 into X plus C1. When X is equal to 0, some rotation is there. Suppose this is theta. This theta, when X is equal to 0, my rotation is not 0. In this case, this is theta. Theta A is equal to theta B is equal to theta. So it will be EI into theta is equal to C1. By putting the value of C1 here, I will get EI into dy upon dx, EI theta. If I integrate it further, then it will be this one. When X is equal to 0, my deflection is 0. My Y is 0. Only rotation I have allowed, my deflection is still 0. When X is equal to 0, it is deflection is 0. By putting this 0 is equal to this 0, 0, 0 plus 0. C2 is equal to 0. So by putting the value C2 is 0 in this way, I will get This is my deflection equation. So from equation 1, at x is equal to L, my rotation is minus theta b. Rotation is minus theta b. This rotation is when x is equal to L means this end. This rotation is anti-clockwise. So anti-clockwise rotation is negative. So I will put this minus theta in the slope equation. In this equation, when x is equal to L, I will get this one. So this is my equation. So m0 plus 2 ei theta is equal to this one. If I put the value of m0 is equal to WL square upon 16. So by putting in this equation, I will get this one, theta. So theta will be WL cube upon 96 EI. So this will be my theta. As rotation is same, so WL cube upon 96 EI. One is clockwise, theta is clockwise. So this rotation is clockwise. Clockwise rotation means theta is positive. And this rotation is anti-clockwise. So anti-clockwise rotation is negative. And both theta A and theta B are equal to each other. Suppose theta WL cube upon 96 EI. So this is the slope. Now it means this slope is, in case of simply supported beam, what is the slope in this case? This was WL cube upon 24 EI. In case of simply supported beam, my this slope is WL cube upon 24 EI. What does it means? My this rotation is 1/4 of this, 1/4 of this. So in case of partially fixed beam, for maximum bending to be as small as possible, rotation is this one, and this is 1/4 of this one. Now if I want to know the deflection, deflection will be obviously maximum at the center. So more for maximum deflection, what I will do, this was my deflection equation. I will put the value of x is equal to L by 2 at the center. My maximum bending moment will be, maximum deflection will be at the center. I will put x is equal to L by 2 in this equation. So I will get EY, y max is equal to minus WL by 2, L by 2 cube, L by 2, 4, and this one. And this is WL square upon 16. So theta I have calculated. So this EI, theta is equal to WL cube upon 96 EI. So by putting all the value in the slope equations, in this equation, I will get this, finally this one, WL4 upon 192, and this is equal to 2/5 of the deflection of a simply supported beam. Simply supported beam, my this deflection is 5 upon 384 WL4 upon EI. So this is 2/5 of this one. So 2/5 of this one is this one. So this deflection in case of fixed beam, partially fixed beam, for this particular case deflection is 2/5. And point of bending moment is like this. So point of contraflexures, these are my 2 point of contraflexures. If I want to know the point of contraflexure, then I will take this moment. This will be WL by 2 into X. This is Hogging minus WX square by 2 is equal to 0. So I will get MX is equal to 0, and this will be my quadratic equations. With this I will calculate the value of the X, and X will be 0.1465 L from A or B, means my this point is 0.1465 from this, and due to symmetry this is also same. These are the distance for the point of contraflexure. Now analysis of a fixed beam, so far we have calculated by double integration method. There is another method which is called flexibility method or force method or method of constituent deformation. With this method also I can calculate the fixed end moment. So what is this? The method consists of identifying the statical redundants from the indeterminate structures and removing the redundant reactions and making the structure statically determinate. What does it mean? Suppose this is the case. So there are 4 degree of I have 4 reactions. One is this, and these reactions. So it is a indeterminate structures of 2 degree. This is MA and MB. So what I will do? First I will remove the redundancy. So this will be a simply supported beam. Then I will remove the redundancy. So this will be by structures. Plus I will add it to this. So these are 2 redundancies. One I will. So effect of this will be like this. So rotation will be there. This is theta A. This is theta B. Suppose if I consider this as a simply supported beam and I apply this moment MA here. So my rotation will be like this. So this will be some kind effect will be, suppose this is theta A1, and because of this is MA, I have applied only MA. So this will be theta B1. Then I will treat it like this and I will apply this MB. So it will rotate like this. This is MB, and this will be theta B2. This is theta A1. So my total rotation at this point will be this algebraic sum of these 3 rotations. Theta A, if I consider this positive down clockwise, then this will be theta A minus this will be anti-clockwise. So minus theta A1 minus theta A2. So algebraic sum of this rotation will be equal to these rotations, and this rotation is equal to 0. This rotations algebraic, so overall effect is 0 here. It means whatever will be the clockwise rotation because of this load, that will be neutralized by the effect of fixed T. So algebraic sum of these 3 rotations and these 3 rotations is equal to 0. So what I have done, first I have made this structure determinate. So this is simply supported beam. Then there are 2 redundants. One I will apply one by one. First I will apply MA, then I apply MB, and I will see the rotations, and then I superimpose all. So this is the method of superimposition, you can say, or flexibility method, or force method. So this method consists of identifying the static redundants from the indeterminate structures and removing the redundant reactions and making the structure statically determinate, which is known as released structure or the basic determinate structure. So this simply put, it is a released structure, basic determinate structure. The displacement of the redundant structures are now found, this theta A, theta B. Now next, the redundant reactions themselves as visualized as load acting on the release structure. This I will visualize as a load released on the release structures. Then I will see the effect, and the corresponding displacement are calculated. This corresponding displacement because of this MA, theta A1, theta B1, and because of this theta B2, theta A2. So corresponding displacement are calculated. The superimposition principle is then applied, and the final displacement due to both the actual load and the redundant reactions must be equal to the sum of those displacement calculated separately. So in this case, suppose had there have been some kind of rotations, then algebraic sum should be equal to that rotations. But in this case, as this is perfectly fixed, so algebraic sum of this will be equal to 0. So this plus this is equal to 0, this plus this is equal to 0. So in case of non-yielding, in this case also, this is non-yielding, the final displacement, deflection or rotation are either equal to 0, or in case of yielding, suppose some rotation is there, then it will be equal to that rotation. So from which the redundant reactions are calculated. So this method is known as the method of consistent deformation, or the flexibility method, or force method. Now figure shows a fixed beam having 4 reaction components, M1, M2, R2, and R2. From reaction of compatibility, which I explained, this one, 4 unknown reactions, so 2 degree of determinant. So I released for release structure, then I will apply this 1. So this theta, which is equal to 0, is equal to so this is equal to algebraic sum of this. It means this theta is equal to this plus this, or theta b is equal to this plus this. So this is equation of compatibility. Algebraic sum of the rotation at A is equal to theta A minus this clockwise, and these are counterclockwise. Theta B is same. So I have 2 equations. Now this is the indeterminate structure, and after removing these reactions, this simply supported beam, rotation will be theta A plus theta B. Then I apply this M1, my rotation will be this theta A1 and theta B1. Then I apply this M2, rotation will be this way. My this theta, which is equal to 0, is equal to this theta, which is equal to 0. This will be equal to this theta clockwise positive, and these are anti-clockwise. Similarly, this rotation is minus anti-clockwise rotation, and this rotation are clockwise means positive. This will be this rotation. finally it will be 0. So I have two equations. From this equation we can find the axis. So as we know, angle of rotation at the ends. So in this case, this theta A is equal to, what is the formula? As I have explained in my deflection of beam chapters, this theta A is equal to WAB upon 6 EIL into L this is the formula, WAB upon 6 EIL into L plus B, means this is A, this B. So rotation is WAB upon 6 IL L plus this distance. Similarly, rotation this theta B is equal to WAB upon 6 EIL into L plus this distance. So this I have explained in my deflection chapter. And because of these rotations, as I have explained, because of these rotations, because this moment, my rotations is this one. So as we know, because of this rotation, my moment is 4 EI. This M1 is equal to 4 EI theta upon L. So because of this, M1 is equal to 4 EI theta upon L. Because of this rotation, this moment is this one. So it means this theta A1 is equal to M1 L 4 EI. And this also M2 L upon 4 EI. So oh, so this is this is not the case. So this was in case of fixed beam. So this is not fixed. This is a simply supported beam. So in case of simply supported beam, my rotation is, this will be ML upon 3 EI. This is the formula. This is simply supported. That was in case of fixed beam. As we know, this diagram will be this one into L. So rotation will be equal to the area of the M upon EI diagram. So this will be M upon EI into L into 1 by 2. So this will be, so this is a conjugate beam. So this is the load. It will act at 2 by 3 of L, and this is the reactions. So to R1 into L. So this R1, which is equal to ML upon 3I. So this is a conjugate beam. So this slope will give the rotation here. So rotation, this will be ML upon 3I. So this is in case of simply supported. So M1 L upon 3I and theta B1, this B1 is equal to, so half of this rotation will come here. So this theta B1 is equal to half of this one. So this is M1 L upon 6 EI. Similarly, this will be M2 L upon 3I, and this will be M2 L upon 6 EI. This theta B1. Then from equation 1, as we know, this rotation should be equal to this plus this. So this is equal to this plus this. What is this? This is m1l upon 3ei. This is m2l upon 6ei. This is half of this one. This is m2l upon 3i. So algebraic sum of this equal to 0 means this rotation which is equal to this one is equal to this plus this. Similarly, this is equal to this plus this. So one equation is this one, another is this one. So I have two equations in the form of m1 and m2. So from this equation, if I solve it, then I will get this one, m2, and by putting the value of m2 in this equation, I will get m1. So m1 and m2 all is equal to this. This is the same which I have calculated by double integration method. So this is a fixed beam, this A, this B. So this is equal to W into this distance into square of this one upon L square, and this is equal to W into this distance into square of this distance upon L square. And this is the same which I have explained, WAB square upon L square, and this is WB into A square upon L square. So reaction also we can calculate. So by taking moment at this, we can calculate the reactions. The reaction will be R1 into L. This is sagging. This is R1, R2, R1 into L minus WAB square upon L square, and this will be also minus WB is equal to this one, and this is also Hogging, means WBA square L square. So this, with this I can calculate the reactions. So reaction will be this WB square upon L cube upon 3 into 3A plus B. R2 will be total downward load, which is W, minus these reactions. I will get R2, and R2 will be this one. Fixed beams, fixed end moments for some standard case. So now let us do the summary. Whatever I have explained, this is the summary of this. This is a fixed beam. So if there is a center point load, then fixed end moment are WL upon 8, WL upon 8. So sagging is positive, hogging is negative. Any of the sign convention you can assume. So this we have described earlier, WL upon 8. In case of eccentric load, it will be WA into B square upon L square, WB into A square upon L square. In case of fixed beam carrying UDL, my fixed beam moment is WL square upon 12, WL square upon 12. When this UDL covers some portion of A, then fixed end moment is equal to WA square upon 12L square into 6L square minus 8LA plus 3A square. So this better it is if you revise, remember this formula, then it will be good. Otherwise you have to calculate it by taking a sum of dx and then integration. So that will take some time. So it is better to keep in mind this formula, so that straightway you can put the value and find the fixed end moments. And this is WA cube upon 2L square for L minus 3L. In case of triangular load, This will be WL square upon 30. This L will be L square upon 20. So it will be less, it will be more. So WL square upon 20, WL square upon 30. In case of this triangle load covers some portion of A, then this moment will be WA square upon 30L square into 10L square minus 15LA plus 6A square. And this one will be equal to WA cube. A is this test upon 20L square into 5L minus 4A. In case of triangular loading like this, intensity is 0 at the ends and it is maximum, then it will be 5 upon 96 WL square, 5 upon 96 WL square. So both the cases, due to symmetry, this is a fixed end moment. In case of a couple which is acting somewhere at a distance A, then it will be this moment into this distance into 3 times of this minus L upon L square. Similarly, this moment will be W and this M into this distance, this is B, this will be M into A upon 3 times of this 3B minus L upon L square. Its rotation will be like this. Its rotation will be like this. So this will be sagging and this will be sagging and this will be hogging. It will try to create hogging effect, try to create a sagging effect. When this M acts at the center, when this M acts at the center, suppose by putting the value of A is equal to B, or you can say A is equal to B is equal to L by 2, I will get this one. This will be M by 4, M by 4, M by 4 and M by 4 will be the moment when it acts at the midspan. And due to settlement, if there is a sinking of delta of this end with respect to this end, then moment will be 6 EI delta upon L square, 6 EI by delta upon L square. Its deflective shape will be like this. This will be sagging, this one will be hogging. Rotation, in case of rotation, partially fixed, suppose this end is perfectly fixed, this is not perfectly fixed, some kind of rotation is there. Because of this theta, moment will be 4 EI theta upon L. This is the applied moment due to these rotations. So its deflected shape will be like this one. So this will be, and this moment will be half of this one. It will be half of this one. So 2 EI theta upon L. So 2 EI theta upon L. So that's it from today's class. So thank you very much. I hope you enjoyed the lectures. Thank you.